Okay, so in 14.2, why am I thinking chapter 10? 14.2, the big topics are doing limits, something we did in 21a, and I suppose also talking about where a function is continuous, where a three-dimensional function is continuous or not. But the big thing is limits. And so quick review from 21a, because it's been a while since we've done limits. First example, limit as x approaches 1 for x squared plus 3x. And remember, your first rule of limits is whatever that number is, even though what a limit means is you're not really at that number. It means you're infinitely close to 1. X is infinitely close to that number. But for all intents and purposes, we just plug in the 1. And if we get an answer, that's it. That's our limit. So your first rule of limits is just to plug it in, plug in the number. Now, of course, those limits are so easy, they never showed up on 21a midterms, right? Just plug in the number and you're done. It was more like a situation like this one or this one. In this example, if I plug in 2 for x squared minus 4 over x minus 2, I get 0 over 0. And that was a big, huge idea, right? In 21a, that's what we called an indeterminate form. Meaning, if all you know about this limit is when you plug in, you get 0 over 0, that's not enough to determine what the value of the limit is. The limit could be a number, it could not exist. There's lots of options. Now, for this one, at the end of 21a, you had a nice way to deal with 0 over 0 limits. What rule did we learn at the end of 21a? Yes, yeah, L'Hopital's rule, right? You could just take the derivative of the top divided by the derivative of the bottom. Well, looking forward into limits with x and y, unfortunately, we will not be able to use L'Hopital's rule when we do these with x and y. So let's acknowledge that definitely works for a single variable limit, but not for multivariable limits. And so what else did we do before we knew L'Hopital's rule? You may recall we just did some algebra, right? We simplified this. X plus 2, x minus 2, factor the top, those cancel. And once those cancel out, then I know I'm not going to get 0 in the denominator anymore. So I just plug in 2 to what's left over, and I end up getting 4 for my limit. So I'll acknowledge that usually L'Hopital's rule, and there'll be times going forward in calculus where L'Hopital, I don't think I have an extra I, is a possibility, but in this case, we're not going to be able to use it. So I'll put or do some algebra is what I always tell my 21A students. Do some simplifying. And then we had limits like this, where we've got a limit as x approaches 2 for a function, but it's a piecewise function. In fact, this wouldn't be too hard to sketch. The parabola x squared plus 1. But we're only sketching this parabola for x values less than 2. So when x, as soon as this gets close to 2, I'd have an open circle there. And if x had been allowed to be 2 here, 2 squared plus 1 would have given me 5. And then to the right of 2, I'd be graphing the line y equals x plus 1, which is a line with a, I guess, a y-intercept of 1 and a slope of 1. So it would look something like this. But if I plug in 2 here, that's going to give me 3. So I can tell that this line actually starts right here. And knowing now what the graph looks like, that to the left of 2, my parabola wants to end at 5, and to the right of 2, my line wants to stop right here at 3, what would we say is true about the overall limit as x approaches 2? D and E, perfect. Yeah, that limit would not exist. And remember that in 21A, you probably wouldn't be allowed to just get away by saying the limit doesn't exist. How did we show that the limit didn't exist? Is we did the limit from the left side, and we did the limit as x approaches 2 from the right side, and we need to show that we get 2 different values. If I plug in 2 here, I get 5. If I plug in 2 here, I get 3. Since those are not equal to each other, I can then say my limit as x approaches 2 does not exist. So there's elements when we jump now into 3-dimensional limits with 2 variables, x and y, which is essentially talking about 3-dimensional surfaces. We're going to see those last 3 examples we did, those we encounter essentially those same situations. Now the notation's a little bit more awkward now because we don't just have x approaching a number, we have y approaching a point, a number too. So we can think of this as we're approaching the point, right? This is a point in 2-dimensional space. I'm getting close to a point 2, 3. And what I want to know, the answer to my limit is going to essentially be my z values, right? My output for this function. And your first rule of limits is you should just go ahead and plug in the numbers. 2 squared plus 3 squared plus 1, 4 plus 9, 13 plus 1 gives me an answer of 14. And all this is saying is, if I think of this function x squared plus y squared plus 1, this is actually a function we've talked about, just saw it earlier. Without that 1, that's a paraboloid opening upward. The plus 1 just moves the parabola up 1 unit. And really all this limit is saying is, as your x and y get near the point, so on the xy plane, think about the point 2, 3, the z value, the corresponding point on my function directly above it, that z value is really getting closer and closer to 14, this z value right there. That's all that's saying. But of course, that's too easy, right? If we just plug in the number, get the answer, yes, you'll have some homework questions on that, but those aren't the ones that are likely to show up on tests, huh? It's too easy. So next one here, limit as x and y approach the point 2, 3, same point. But now I have 9x squared minus 4y squared divided by 3x minus 2y. If I plug in, let's just do the math in our head. If I plug in 2 for x, this is going to be 4. That's going to be 36. This will be 3 squared is 9 times 4 is also 36. So I'm going to get 0 on the top. 6 minus 6, I'm going to get 0 on the bottom. And this is where I'll acknowledge no L'Hopital's for limits with more than one variable. How about that? Sad face. Okay, because L'Hopital's rule, we came to depend on that, right? That was so nice. Just take the derivative. We didn't even have to worry about algebra anymore, right? Which means our only option right now, well, okay, our first option we should try to do is kind of like the example we did up here. We should try to simplify this, doing some algebra. And hopefully you see this one. I could factor the top. This is actually a difference of squares. 9x squared minus 4y squared factors into 3x plus 2y times 3x minus 2y. And that allows me to cancel out the denominator. And once that happens, if I plug in 2 for x, so 3 times 2 plus 2 times 3, 6 plus 6, my limit will be 12 in this case. Remember that doing some algebra, sometimes it's factoring. If you've got limits with square roots, it might be multiplying top and bottom by the conjugate, right? So there's more than just factoring. You might have to find a common denominator or something like that. So some kind of algebra. So I'll just put do some algebra again. So because these involve a little more work, more likely that a problem like that would show up on a quiz or an exam. But what is almost a sure thing that will show up on your next quiz or exam having to do with limits, it would be one like this, and the next several we're going to do. Because here I have x and y approaching the origin, basically 0, 0, 4xy over x squared plus y squared. If I plug in 0 for x and 0 for y, I'm going to get 0 on the top and 0 on the bottom, which we just saw, right? But what's the problem? I don't see any algebra that's going to simplify that out and cancel anything out. But we cannot simplify this with algebra. So here's the deal. In 21C, if you get a limit that is 0 over 0 and you cannot simplify it with algebra, we are going to now operate on the assumption, unless we're told otherwise, we're going to assume that this limit does not exist. Okay. If you cannot simplify with algebra, so unless, I can't spell unless indicated otherwise, assume the limit does not exist. DNE. And you might be saying, well, wait, what if the limit did exist, right? And as we do some of these, you'll see why you kind of have to make that assumption. Otherwise, we're going to be in for a long ride. Okay. And I have had teachers who have mistakenly given a problem like this where the limit actually does exist and did not tell the students that the limit existed, and it causes all kinds of problems. Let me show you why. So if we're going to assume that the limit doesn't exist, we need to justify that. And it comes back to this example here. In a 21A example, what proves the limit doesn't exist is that if x approaches 2 from the left side, I can see my y value is getting close to 5. If x approaches 2 from the right side, I can see my y value approaches something different, right? That these don't agree with each other. So we're essentially doing this. We're going to try to show that if we approach our point from 2 different directions, that we're getting 2 different answers. But there's a big difference here. Now it's not just x approaching 0, but it's y approaching 0 as well. So what we want to think about a different color here. Here's 0, 0. In 21A, since we were only playing around with x, all we could do is move along the x-axis. We could have x approaching a number from the left and the right. But now that we get to get y involved, not only could we approach 0 from the origin along the x-axis, in other words, having x approach 0 from the left and the right, we could approach along the y-axis, right? Because y is getting close to 0 as well. In fact, we can approach along any pathway, any equation. So like right here would be the x-axis has the equation y equals 0. The y-axis has the equation x equals 0. What about a line that passes through the origin, like y equals x? We can get close to 0, 0 along this line. We could get close to it along y equals negative x. Y equals 2x, 3x. What about y equals x squared? That goes through the origin, so I could certainly imagine my x and y getting close to 0, 0 along this pathway, negative x squared, x cubed. The point is, how many pathways, how many equations of graphs can you think of that go through the origin? How many people agree with infinite? There's an infinite number of graphs that pass through 0, 0. Okay. Our job now, if this limit doesn't exist, all we need to do is find 2 pathways, any 2 of these that give me 2 different answers for my limit, and that would be enough to prove that the limit doesn't exist. But we have an infinite number of pathways. Maybe I could. We check pathways that go, in this case, through 0, 0, because that's where our x and y was approaching. And so this is what it looks like. If I approach 0, 0 along, let's start with along y equals 0, along the x-axis. Here's how this works. Whoops. So I have x, y approaching 0, 0, but I'm going to be letting y be 0. So I could say x comma 0 approaches 0, 0 for 4x. Okay, if y is 0, this is just 0, isn't it? Y is 0 over x squared plus 0 squared. This is going to just give me 4x times 0 is just 0, and my denominator is x squared. And if x approaches, well, it doesn't matter. 0 over anything is going to be 0 here, right? Or you know what? Hey, let me time out. See if I can sneak this in here. Technically, I should have one extra step here. Once I plugged in y equals 0, I still had an x left over, but now I could just, since there's no y anymore, I could just say, what's the limit as x approaches 0 here? And to clarify this, this used to bother me, so I have to imagine this might bother some of you. What happens if I plug in 0 for x? Because I just told you that's how you should do a limit. Doesn't it seem like it's a 0 over 0 limit if I plug in 0? And we just had a whole discussion that 0 over 0 is an indeterminate form. And yet I'm claiming the answer is 0. So I can see there's a little bit, what seems like a little bit of a contradiction here. But here's the difference. When we talk about indeterminate forms and limits, let's go back to this one, the second one we did here on the 21A review. When we plug in 2 at the beginning and I write 0 over 0, remember how this works. I don't mean this is literally 0 over 0. What I mean is it's approximately 0 over approximately 0. Why approximately? Because this doesn't say x equals 2. This says x is close to 2, right? So in reality, what's happening when we plug in a number like 2.000001, we're getting approximately 0 on the top and approximately 0 on the bottom. And that's what we mean by indeterminate, when something is close to 0 over close to 0. Here's the difference. This isn't the same thing. Because while the denominator, if x is approaching 0, this is approximately 0 on the bottom. This is not approximately 0 on the top. Why? Because we were told y equals 0, not a close to 0, y equals 0. And 0 times anything is exactly 0, right? And exactly 0, even over something that's really small, will be 0. So there's no contradiction there, right? If I did, this is kind of like, if I did 0 over 0.00000001, well, that's still 0, isn't it? Because my numerator is 0. My goal now is to, so I know now that if we approach this function along y equals 0, my limit is 0. My goal now is to find one of these other pathways and show that I get something different than 0, right? Because we're trying to show that the limit doesn't exist. How many people can see that if I tried x equals 0, if I put 0 in for x here, that would be 0, that would be 0. I would end up with 0 over y squared, which would also be 0. So that's not going to help me. So usually I would try y equals 0 and then x equals 0, but that's not going to help me. So let's try, how about y equals x? So I have x, and since y is x, I could have x comma x approaching 0, 0. If I plug in x for both of my y's, notice this now just turns back also to just a regular old x limit, where the numerator is 4x squared. The bottom is x squared plus x squared is 2x squared. Those end up canceling, and I get an answer of 2. And that's what I was going for. Based on these two limits being different, I can now say that my overall limit, I guess I should be thorough. How about I just put f of x, y, though, for that instead? Does not exist. So this is how we're going to handle it. And like I said, these are the real common ones. You will no doubt, I could promise money almost that you'll get one on your next quiz or test or final if that's the next exam. So we should practice some more of these. Limit as xy approaches 0, 0, 8xy squared over x squared plus 3y to the fourth. If I put 0 in for x, 0 in for y, I'm also going to get 0 over 0. But there's no way I can simplify it, right? But no algebra works. So we're going to then assume that the limit doesn't exist. Assume DNE. And now we're going to have to back that up by finding pathways, doing this limit along different pathways and showing that we get two different answers. A lot of these kinds of limits where you have to do the two pathway test have X and Y approaching 0, 0. I do have one coming up where it's not, but a lot of them do, but don't always just, you know, they're not always that, but. Now, a natural question to have here is, we agree that there's an infinite number of pathways that go through 0, 0, right? We talked about y equals 0, x equals 0. Last time I did y equals x, right? And so what I'd always do is I usually start with y equals 0 or x equals 0 just to get a benchmark, right? Some kind of a baseline of what a limit, and then I can try to find something that gives me a different limit. So let's approach along y equals 0. And now that you see what I'm doing, to try to shorten this up a little bit, if you replace both of your y's with zeros, can everybody see, first of all, it's now there's no more y's, so I'm just going to let x be 0, approaching 0. And all that's going to be on the numerator is 0, and all that's going to be left on the bottom is x squared. And like we said before, 0 over anything is 0. Similarly to the last one, if we let x be 0, it would make my numerator 0 and my denominator 3y to the 4th. I would also get 0, so that would be a waste of time. Let's try the one that worked for us last time that gave us something different. Let's try along y equals x. I want to show you what happens here. And I'm just going to be plugging this in my head, and I'm going to just turn this into just now x approaching 0. If y is x, this numerator is going to be 8x cubed, and the denominator is going to be x squared plus 3x to the 4th. Which is, right now, it's still 0 over 0, but I can do some algebra on this, right? I can factor out an x squared from the bottom, which I could then cancel and knock this down to just x to the 1st here. But what happens if I plug in 0 now to what's left over? I still have an x there, right? I still have this 8x. So I'm going to get 0 on the top, and I'm going to get 1 plus 0 on the bottom. And so I end up with 0 over 1, which is still 0. So that's not helpful. It's not helpful, right? I mean, I needed to go down this road so I could see this, but what I'm going for is something that gives me something different than 0. And what could very well happen, this is what I mean by when I said, unless they tell you otherwise, you have to assume the limit doesn't exist. We could try something like y equals negative x. I think I had that there. Guess what? You're going to end up getting 0. You could try a different line through the origin, like y equals 2x. I'm going to already tell you, if you try that, you're going to get 0. You could try 10 different pathways and keep getting 0. And how many people agree that you would start to maybe think, maybe this limit does exist, and maybe the answer to the limit is 0, right? If you tried 10 different pathways and kept getting 0, I'd probably start to think that maybe the limit is 0. But remember, you are only trying 10 pathways out of how many pathways? There's an infinite number of pathways. Infinite number of equations I could think of that go through the origin. How about sine of x, right? Sine of x goes through the origin. All it would take is one pathway that gives me something other than 0, and all of a sudden the limit would not exist. That's why it would be unfair if this limit actually exists. They need to tell you, because otherwise we're going to operate under this assumption and we're going to be checking limits forever. Okay. Now, the next thing you're probably wondering then, okay, Grant, well, then I don't want to test 10 pathways. What's the secret to determining a pathway that's going to give me something other than 0? That's not approximately, well, it's infinitely close to 0, so the limit is 0. Here's the secret. And let me just do it, and then you'll see why this works. The pathway I'm going to choose is x equals y squared. X equals y squared, by the way, that is a sideways parabola. Goes like this. I'll explain in a minute, but let's see what happens. If I replace my x's with y squared, now I'm going to have just y, so it's just going to be y approaching 0, and I'm going to get 8 y squared goes in for x times y squared over my x is y squared, so this is going to be y squared squared plus 3y to the 4th. And if I combine, I get 8y to the 4th over, this is y to the 4th plus 3y to the 4th is 4y to the 4th. And lo and behold, I get 8 over 4, which is 2. And now I've shown why this limit doesn't exist, because I got 2 different answers. So now let's analyze, why did that work? Why did that work? If you think about it, what was good about y squared is when I plugged it in, what happened? I got the same degree on the top and the bottom, right? That's how you know. You're trying to figure out what you would plug in to get the same degree in the top and the bottom. They don't tell you that in the book, so that's a secret between you and I. Okay. All right, and then I threw in one here just to make sure we don't get too lackadaisical. And well, let me first of all plug in. If x is 1, y is -1. This is -1 plus 1 is 0. 1 plus -1 is 0. We've just done 2 in a row, and I'm sure you've done some in class if you're there, where x and y is approaching 0, 0, right? And I don't want anybody walking out of here saying, hey, okay, when I get 0 over 0, I should try x equals 0, y equals 0, y equals x, all of these things here. These only are my choices because they pass through 0, 0, right? Here now I have one where my limit is a point, 1, -1. It's like right here. Yeah. And again, because there's no algebra I can be done, right? No algebra. So we're going to conclude that the limit does not exist, most likely. But now we have to prove it. But what paths can I choose? See, I can't choose y equals 0 or x equals 0 because those don't pass through my points. What I can choose, kind of the equivalent, this line right here would be y equals -1. X equals 1. If I need more, I could use this line, couldn't I? This line right here would be like y equals -x. That goes through that point. So there's options. If y is -1, this is going to be -x plus 1. And the bottom is going to be x minus 1. And negative x plus 1 is the same thing if I factor out a negative of negative quantity x minus 1. So that limit's going to give me negative 1. And I don't think we're going to have to use y equals negative x, because I think if we plug in just 1 for x, one for x is going to give me y plus 1 over 1 plus y. And those are the identical, right? Those just cancel. So my limit is 1. And so, yes, I've now proven it, right? That this limit does not exist because I got two different answers. Another option that I know some people have had to consider, if you're not to 14.2 yet, you may or may not do this. This is kind of an optional thing that gets covered in 14.2, is some of these limits actually are easier if you run them in polar coordinates. And having said that, let me also mention that 21D, I told you that this section of 21C is all leading towards 21D, where we work with vectors, we work in 3D, but also pretty early on in 21D, we do things in polar coordinates. How many people covered polar coordinates in 21B? It's technically in the syllabus for 21B, but it's kind of at the very end. And my experience is about 50% of 21B classes actually get to it. A lot of the other 50%, they run out of time, the quarter's over. Challenor did. Okay, that's good. That's good. So you have some experience with it. Yeah, I think it's a mistake to skip that in 21B, because 21D, they often just assume you're already somewhat proficient with polar coordinates. But then people who didn't get it covered in 21B, it's not as it might be something new. So let me do a quick lesson on polar coordinates. Polar coordinates is an alternative to Cartesian coordinates, which are the way we normally graph things. If you want to plot the point x, y, starting from the origin, you go over x and then up y, and that takes you to the point x, y. But in polar coordinates, maybe even a little more natural in terms of like real life, like let's say, okay, some of you are on campus. I'm thinking the first picture that came to mind is the quad. Let's say you're at the like Shields Library. If you've been there, there's an intersection of two bike lanes, and then this is the quad. And the coffee house where you can get a nice drink is over here. So if you were right here and you wanted to get to the coffee house, and this is all nice grass, it's easy to walk on. How many people maybe wouldn't go this way and this way to get to the coffee house? What would you do? Assume you were facing this way, because remember, like in trig with the unit circle, that is an angle of 0 facing the positive x-axis. What I would do to get to if I was really thirsty, is I would just face myself the correct angle that points me to the coffee house and then just go straight there, right? Rather than taking the long way. That's the idea of polar coordinates. You need to give me two things to locate something. You need to tell me what theta is, what that angle is, and then how far to proceed, which is what we call r. So in polar coordinates, instead of x, y, we define a point by r theta. And there's some important conversions with polar coordinates. For one thing, just looking at this picture, by the Pythagorean theorem, x squared plus y squared would have to equal r squared. If you did, for example, the cosine of theta, that equals adjacent over hypotenuse, x over r. So if I wanted a replacement for x, x is equal to r cosine theta. Okay, good to know. Thank you. I didn't know that. Okay. So it looks like other classes have talked about polar coordinates as well. Sine of theta is y over r. So y is equal to r sine theta. I think these are pretty much the main conversions you need to know. Let me give you one example though. For example, if I had the point 1, 1, let's just do that, where this is x, y, and I wanted to convert that to polar, just slide this up. You know, based on the picture that I just drew there, instead of going over 1, up 1, you would have to find out what this angle is, but that's not too hard, right? If this is 1 and this is 1, that angle would be 45 degrees or pi over 4. And then you need to know this distance right here, but by the Pythagorean theorem, that would end up being √2. So in polar coordinates, this would end up being √2 pi over 4. You put r first and then theta. So that's just a mini lesson on polar coordinates. Okay, so you can run some of these limits in polar coordinates. I would first plug in. If I plug in, I end up with 0 over 0, and it's another one of those where I can't do any simplification here, right? And now, yeah, oh, good. I'm glad I put this one on here. I'm seeing what's going to happen. Because earlier I told you to assume that this limit does not exist if you get 0 over 0 and you can't do any algebra. So maybe for this one, I'll put note the limit exists. So let's convert this to polar coordinates. We'll get to this in a second here. And how you would do that is you could use your replacements, your conversions. I know x is r cosine theta, so I could, for x, I would have r cosine theta squared times y. Y is r sine theta. X squared plus y squared literally is r squared, so I could just put that there. But now check this out. Unlike a point like 1, 1 or something over here or a point over here where you're going to have to give me an angle and you're going to have to give me a distance. But if I'm at the origin, because isn't that where x and y is approaching, right? At the origin, in polar coordinates, remember you basically start at the origin, and what we first are supposed to do is figure out what angle we need to move to be facing to get to where we want to go. Well, can you see that if I'm at the origin, it doesn't matter what angle you move, just don't go anywhere, right? If I just stay put, I'm going to be at the origin. So in other words, 0, 0 in polar coordinates is basically 0, any theta, right? Any angle will work, just as long as your r is 0. And so because of that, what we get to do here is when we write this in polar, it's just a single variable limit. Getting close to 0, 0 is the equivalent to just letting r approach 0. R equals 0. Does that make sense? Now, if I simplify this, clean this all up, can you see if I square this, I'm going to end up with an r squared times an r. I'm going to end up with 3r cubed times a cosine squared theta times a sine theta over an r squared. R squareds cancel with that r cubed, leaving me with still an r. And then here's the idea. if you plug in 0 for this r, we don't know what theta can be anything, but does it matter? If this thing goes to 0, 0 times the rest of this junk is going to be 0. My limit is 0. Which is why, now let's revisit what I said earlier about assuming when the limit doesn't exist. What the implication that this is the limit is this. If I didn't tell you that the limit existed, and if you didn't switch it to polar, and we knew that we couldn't do any algebra, and I started doing some testing, like picking pathways, like we did earlier, guess what would have happened? If I had picked pathways, I approach here, 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 parabola, sideways parabola. Guess what my answer would have been every single pathway I would have chosen? What would my answer have been? It would have been 0. And the trouble with that is, remember that if we were operating under the assumption that the limit didn't exist, we may be thinking, am I missing one? All it would take is one pathway I haven't thought of to make the limit exist, right? So you'd be checking pathways forever. That's why, in my opinion, they have to, well, either tell you to run it in polar coordinates because that worked out whether or not we were told or not, right? Or tell you that the limit exists if it does, because otherwise you might be doing pathway testing forever. So. And just one more here. I think that was my problem I did a couple problems ago. Yeah, we already did this limit, and we were able to show with pathways that the limit doesn't exist. Let's see how this works with polar coordinates. Once again, approaching the origin is the equivalent to r just approaching 0. And if I plug in my conversions, x squared plus y squared equals r squared. I'm going to get 4r squared cosine theta sine theta over r squared. The difference here, what happens is my r squareds cancel completely, and I don't have any more. I don't have any place to plug in the r equals 0, so my limit is 4 cosine theta sine theta. And what do I know about this is this could be, I can get different answers, right? Lots of different answers. Depending on theta. So for example, if theta is equal to, I don't know, 0, my limit would have been cosine of 0 is 1, but the sine of 0 is 0. My limit would have been 0. But if theta had been, for example, pi over 4, cosine of pi over 4 is root 2 over 2. This one's root 2 over 2. That's, if I multiply them together, it's 2 over 4. It's 1/2. It would end up being 4 root 2 over 2 times root 2 over 2 is 4 times 1/2. My limit would have been 2. And see, that would have been enough to prove that the limit doesn't exist, huh? So the limit doesn't exist. Okay, enough of limits. Enough of limits. Let's get to more important stuff, which is partial derivatives. So in the 20 minutes or so I have left,